everybody. Today we are going to start the three-dimensional geometry. This chapter, the sphere from three-dimensional geometry. Hmm. What is sphere? Sphere is actually a three-dimensional surface. Actually, a surface in three-dimensional space. Hmm. And it is a surface generated by a point P such that this point P always maintains a constant distance, maybe let us call it small a, a constant distance from this fixed point C. This fixed point is called the center of the sphere, and this a is called the radius of the sphere. Hmm. And in this kind of if suppose P has this kind of coordinates x comma y comma z, as because it's a point in three-dimensional space, therefore it should have three coordinates x y z. And suppose C has this kind of coordinates x1 comma y1 comma z1, and the radius has been taken in over here in place of a, the radius has been taken over here as equal to small r. All right. So this distance Cp must be is equal to this r small r, or Cp square is equal to r square. Cp square means x minus x1 whole square plus y minus y1 whole square plus z minus z1 whole square. That would be is equal to the distance r square. So this is the equation of the sphere. Equation of the sphere is x minus x1 whole square plus y minus y1 whole square plus z minus z1 whole square is equal to this kind of r square. And this equation, if it is further simplified, this equation can be converted into this kind of form: x square plus y square plus z square plus twice gx plus twice fy plus twice hz plus c is equal to 0. You can compare this equation with the equation of a circle in two-dimensional geometry. In the equation of the circle, we did not have this kind of term z square, and we did not have had this kind of twice hz. Only this is the difference. So whatever result you studied in case of circle in two-dimensional geometry, most of these results would be true over here. Along with that, as because the dimension is a bit is three-dimensional quantity, therefore some extra result would also come in this chapter. So for reference, it is better to think about a circle in two-dimensional geometry. Similar properties would hold over here for sphere in three-dimensional geometry. Okay. And this kind of equation, you see, this kind of equation can be written over here like this: x plus g whole square plus y plus f whole square plus z plus h whole square, that is equal to g square plus f square plus h square minus c. So we can say that this equation will ultimately represent a sphere with center. What would be the center? Center would be minus g. Minus g would come from this factor. If you compare this equation with this standard equation of the sphere, then we had over here actually x coordinate of a point minus x coordinate of the center. So compare it, x coordinate of a point on the sphere minus of minus g, that would be is equal to plus g. Okay. So over here the x coordinate of the center would be is equal to minus g. Similarly, y coordinate of the center would be is equal to minus f, and z coordinate of the center would be is equal to minus h. So in this way we can find the center of the sphere. And what would be the radius? Radius would be the square root of right hand side, positive square root of right hand side, that would be the radius of the sphere. So it is clear that the sphere would be a real sphere provided this expression within this square root symbol, that expression is greater than is equal to 0. If by chance this is less than is equal to 0, then there is no such sphere at all. All right, or we can theoretically say that the sphere would be an imaginary sphere. Hmm. Just like an imaginary pair of straight line we discussed in case of two-dimensional geometry. So that is the condition that under which this kind of given equation, would represent a sphere, a real sphere. Okay. So this is the equation about the sphere, and if you consider the general equation of second degree, you see over here this is a general equation of second degree involving three variables. Okay, over here x square, y square, and z square related term is there are three different terms, and in this next three terms we have yz, then zx, and then xy. In this term, x is absent. In this term, y is absent. In this term, z is absent. So all these three terms, along with the first three terms, so altogether all these six terms, these are all second degree term involving three variables, x, y, and z. Okay, and twice ux plus twice vy plus twice wz. This is actually first degree term involving three variables x, y, z, and along with that we have a constant term. So in this way we construct the general equation of second degree involving three independent variables x, y, and z. So if you compare the equation of the sphere with this equation, then you see over here this coefficient a, this coefficient b, and this coefficient c should be same. Over here, if you look at this, expression, all these coefficients of x square, y square, and z square, all these coefficients are same. Even over here, all these coefficients are equal to 1. Hmm. So over here, all these coefficients must be same. A, B, C must be same. Hmm. And if you look at this equation over here, no xy related term, no yz related term, no zx related term is there. Hmm. Therefore, we can say that the coefficients of this xy, yz, and zx, these three coefficients must be is equal to 0. So f, g, and h, that should be is equal to 0. So this is the condition under which a second degree equation involving three variables must represent a sphere. And remember over here, a, b, and c are equal to 0, and all of them must be non-zero quantity. The coefficient of x square, coefficient of y square, and coefficient of z square. These three coefficients must be same and non-zero. Otherwise, this kind of terms would be absent. And in that case, it would not form any sphere at all. Alright, that's why we have this kind of condition, A not equal to 0. It means that B not equal to 0 and C is also not equal to 0. So these are the conditions under which a general equation of second degree involving three variables represent a sphere. Okay. Now we are going to discuss different kind of form of this sphere. Suppose consider analogous result for two-dimensional geometry. In two-dimensional geometry, what we had a circle, suppose, and we can now consider this circle as a sphere in three-dimensional geometry. And in this sphere, let us consider the radius. This is suppose the radius of the sphere. If we know the coordinates of this endpoint, suppose this one endpoint is equal to a, another endpoint is equal to b. Okay, these are two endpoints, suppose. And if capital A has this kind of coordinates x1, y1, z1, and capital B has this kind of coordinates x2, y2, z2, then we need to find out the equation of this sphere. If we know the equation of these endpoints of the diameters A and B, then we need to find out the equation of this sphere. Then how can we find the equation? Let us first consider any point, suppose P, on the sphere. And in that case, we can consider the coordinates of the point P as x, y, and z. Now let us draw two straight lines. Just join these 2 points A, B, and over here PB. If we join these 2 points, in that case, these two straight lines AP and BP. These two straight lines we'll have the direction cosines, and how to compute the direction cosines of these two straight lines. You see, if we want to consider the compute the direction cosine of the straight line PA. Okay, the direction cosine of the straight line PA. In that case, how do we find the direction cosine? We generally subtract the coordinates of one point from the another point. Okay, the coordinates of the point P. The coordinates of the point P are x, y, and z. These are the coordinates, and the coordinates of the point A. These are the coordinates x1, y1, and z1. Okay, so if we subtract these coordinates, then we'll get x minus x1, y minus y1, and z minus z1. This would be the direction ratios, particularly the direction ratios, not necessarily direction cosines, the direction ratios of the straight line PA. And similarly, we can find the direction ratios of the straight line PB, one quantity minus another quantity, the coordinates of the point P minus the coordinates of the point B. So over here in this x minus x2, y minus y2, z minus z2, these should be the direction ratios of the straight line PB. Okay, and if this AP and PB, these straight lines are, you see, as because capital A and capital B, these are two endpoints of the diameter, then we know that this angle must be a right angle or 90 degree, or pi by 2 radian. Okay, therefore we can say that this straight line PA and the straight line PB, they are perpendicular to each other. Okay, and as because they are perpendicular to each other, therefore the direction cosines, if you consider the dot product of these direction cosines, consider this direction cosine as a vector and these three direction cosines as another vector, then the dot product of these two vectors must be is equal to 0. So over here we can say that x minus x1 multiplied by x minus x2, this expression, hmm, this expression, plus y minus y1 multiplied by y minus y2, then this expression y minus y1 into y minus y2, plus z minus z1 into z minus z2, this kind of expression, that total sum must be is equal to 0. Okay, so this is the equation of the this would be the equation of the sphere having the endpoints capital A and capital P. This is just very similar to the expression of equation of the circle in two-dimensional geometry. Whenever we know the endpoints A and B, we know the coordinates of the endpoints A and B. Okay, so in this way we compute the equations of the equation of the sphere. Now let's consider the equation of a circle. If you consider the cross section of a sphere by a plane, you see this is the plane z is equal to 3, and whenever you see this is the plane z is equal to 3, this kind of plane is the plane z is equal to 3. And if we now consider the section, you see this would be the section of the this would be the section, this would be the section of the of this plane or section of the sphere by this plane. Okay, so this is actually a sphere, and this is actually a sphere, and its section would be a circle. That section would be clear whenever consider this kind of you consider this kind of view. So this kind of expression, this kind of circle equation of this kind of circle has to be found. And over here you see, if you consider the equation of this kind of circle, in that case what you need to do, we need the equation of the sphere as well as the equation of the plane. The equation of the circle is considered as a collection of the sphere and the plane. That would be the equation of the circle. So equation of the circle will be represented in this way. You see, equation of a circle. So let us consider this kind of sphere: x square plus y square plus z square plus twice gx plus twice fy plus twice hz plus d is equal to 0. So if this is the equation of the sphere, say this is the equation of the sphere, and let us consider the plane ex plus by plus cz is equal to p. Okay, this would be the equation of the plane. All right. Now, if we consider the, let us draw the picture over here. If we consider this kind of say this is the sphere, and suppose let us draw one section. Say this would be the section of the this kind of section. This would be a circle on the sphere. So what kind of circle? You see, that is actually the very the section of this kind of plane. hmm, Section of this kind of plane. Okay, and we are interested to find the equation of this section. That would be actually a circle. Hmm. So over here we need to draw the equation of the circle. And how to draw the equation of the circle? That would be the collection of that would be drawn by and the help of this sphere and the this plane. Okay, therefore the circle will be represented jointly by these two equations, the equation of the sphere and equation of the plane. That would be the equation of a circle. Okay, now let us consider the intersection of two spheres. Let us consider the intersection of two spheres. Okay, let's draw one sphere. This is suppose one sphere, and this is suppose another sphere. This, it might be a bit larger, this kind of sphere suppose. And now we are interested to find out the circle of intersection of these two spheres. Okay, this would be the circle of intersection of these two spheres. And in the back side, it would also have a intersecting zone. So this would be the circle of intersection of these two spheres. And suppose the equation of the sphere is s is equal to 0, and the equation of the second sphere is s prime is equal to 0. And in that case, how to obtain the equation of this plane of intersection? This would be the plane of intersection. Hmm. This would be the plane of intersection. Okay, this would be the plane of intersection on which this circle will be generated. This would be the plane of intersection on which this circle will be generated. So how to obtain this plane of intersection? You see, this is the equation of the plane, and over here the coefficient of x square plus y square plus z square, the coefficient is always equal to 1. Similarly, in this second sphere as well, the coefficient of x square, y square, and z square, this plane would also be equal to 1. Got it? Therefore, over here, s minus s prime. If you consider the difference, s minus s prime, then this term and this term will get cancelled. And then this difference, this would, it would be twice g minus g prime into x plus twice f minus f prime into y plus twice h minus h prime into z plus c minus c prime is equal to 0. You see, if you look at this picture, if you look at this equation, you will find that this is actually the equation of a plane. And that would be the plane of intersection of these two spheres. Okay, so this would be the equation, plane of intersection of the spheres given by equation 1 and equation 2. Okay, so this is the plane of intersection of these two spheres. Now, you see, sometimes we need to compute the equation of a sphere whenever a sphere is passes through a circle. Suppose we have a circle. say this kind of circle. Okay, say this is the circle, and the circle may lie on this kind of plane. Now we need to draw the equation of a sphere. We need to draw a sphere, this kind of sphere. We need to draw a sphere like this, which will pass through this kind of circle. Sometimes we are interested to draw this kind of circles as well, this kind of sphere. Say maybe this is the maybe this is the sphere like this. Yes. Hmm. So we are actually interested to find the equation of this kind of sphere which will pass through a given circle. All right. So how is it possible? And it might be possible to draw by this kind. A circle might be possible to generate by the equation of a sphere. Let us consider the equation of a sphere. Let us denote it by another color, say green color. Hmm. And then let us draw this kind of equation. Say this is the sphere through this circle. Hmm. So sometimes it may so happen, suppose this over here, let us consider this kind of sphere. Say, you see, this circle can be considered as a section of this sphere and this plane. So circle can be given as the section of a sphere. This might be the sphere S, and this might be the plane L. So surface can be considered, a circle can be considered as the section of this kind of sphere S and this kind of plane L. Okay, so circle can be considered by this kind of intersection of a sphere S is equal to 0 and L is equal to 0. Hmm. And suppose we are interested to compute a sphere passing through this circle, then what would we do? You see that can be obtained by this kind of expression. You see that would be actually that would be actually a surface passing through this curve of intersection. This sphere, this circle is actually the curve of intersection of this sphere. S is equal to 0 and L is equal to 0 is the plane. So this circle can be considered as the curve of intersection of this sphere. S is equal to 0 and L is equal to 0. And therefore this their any surface through their curve can be written in this way: S plus lambda into L is equal to 0. So S plus lambda L is equal to 0 would be the equation of the sphere passing through this given circle. That circle is actually the curve of intersection. Now let us consider the section of a sphere with a given center. You see, suppose C is the center. C is the center having coordinates A, B, and C, and we are suppose given the coordinates of this point center. And if we know if we know the equation of the coordinates of this of the center of the sphere. You see, this C is the center of this circle, and that is actually a small circle. And this kind of point O, that is the center of the sphere. What is a small circle and what is large circle? You see, whenever you consider this kind of sphere, and you may consider a circle like this kind of circle that is passing through the center of the sphere. Okay, this kind of circles are called great circle. Remember these two definitions. This kind of circles are called great circles. And what is a small circle? When any circle on the sphere other than this great circle, that would be called as a small circle. So this is the idea of small circle. This is the distinction between great circle and small circle. Now suppose this is this point O is the center of the sphere, and this point C, this is the center of this small circle. Okay, and say this is the point P lying on the sphere. Now, if we know the center, or if we know the coordinates of the point C, suppose A, B, C, these are the coordinates of the point C, and O, this point O is the point 0, 0, 0. Okay, this point O is the point 0, 0, 0. That means the origin. All right. So this O refers to the origin. In that case, what would be the direction ratios of the point OC? The direction ratios of the point OC would be is equal to A minus 0, comma B minus 0, comma C minus 0. These three would be the direction ratios, that is actually A comma B comma C. These three would be the direction ratios of the straight line OC. Okay, and you see this straight line OC, this straight line OC, and the straight line PB. This straight line OC and the straight line PB over here, you see this angle must be is equal to 90-degree angle. So that angle should be is equal to pi by 2. Okay, and what would be the direction ratios of the straight line CP? If suppose P is the P has this kind of coordinates x comma y comma z, hmm, x comma y comma z, then direction ratios of CP, the direction ratios of the straight line CP would be is equal to x minus a, y minus b, and z minus c. These three would be the direction ratios of the straight line CP. All right, and therefore, as because this angle is a 90-degree angle, therefore the dot product of this direction ratios and this direction ratios, the dot product of the direction ratios of OC and the direction ratios of this straight line PC, both these two dot product, that must be is equal to 0. So in this way we will be able to compute the equation of the plane. Which plane? The plane on which this small circle will lie. We will be able to compute the equation. We will be able to compute the equation of the plane. This plane. Then the equation of this circle, this small circle, the equation of this small circle can be written as the intersection of this plane and the intersection of this sphere. Got it? So in this way we will be able to find out the section of the sphere with a given center. If the coordinates of the point of this center C are provided, in that case we will be able to find out the section of this kind of plane. Let us consider this example. This is an important example over here. You see, what we need to do, we need to find the equation of the sphere for which the circle x square plus y square plus z square plus 7y minus 2z plus 2 is equal to 0 is a great circle. Sometimes if you want to clearly draw the pictures, let's it would not always be possible to draw this kind of picture. You need to imagine this kind of pictures because these are actually three-dimensional picture. But let's try to compute the equation of this plane and the equation of this sphere through this kind of software. Let's see. So this is the sphere. Hmm. And now let us try to draw the equation of this plane. Twice x plus 3y plus 4z is equal to 8. You see, this would be the section. Hmm. Let us try to change the color of this equation. Let us try to change the color of this plane. Say consider this kind of color. Okay, so you see, you can check that this kind of section, that is actually the section, the sphere, given sphere. Hmm. And this kind of section would be the given sphere. Let me maximize this one. Hmm. This is the given sphere. Okay, that is the sphere given by this kind of equation: x square plus y square plus z square plus 7y minus twice z plus 2. That is along with this plane twice x plus 3y plus 4z is equal to 8. This is the equation of the, this is the required great circle, and we have to find out a sphere such that this circle becomes a great circle. Now how to find out the sphere? Hmm. Over here, we already computed the equation of this sphere. This is the required equation. So x square plus y square plus z square minus twice x plus 4y minus 6z minus 2 plus 4 minus 6 plus 10. So this would be the this red sphere. You see this red sphere. Hmm. This is the sphere. Let us try to change the color. Okay, let us try to change the color to this green color. So this green color, this is the green sphere is actually a sphere which has a great circle as the, and that this great circle is actually the intersection of this given sphere, the first sphere, and this plane given by this kind of curve. Hmm. So hopefully this is clear to you. Hmm. And so this is the, this is this and the sphere and the circle was given by the intersection of this sphere and this plane. Hmm. And this is the required sphere. All right, so in this way we compute the equation of this green circle. This is the required sphere. All right, so in this way we compute this equation. So all different kind of spheres, all these kind of problems cannot always be shown by the help of this kind of computer programs. You have to think of it, and in this way you will have to go through these problems. So we already defined a great circle. Let us try to draw the picture over here. Suppose this is a circle, and we want to find out the equation of the great circle. Hmm. And suppose this is the plane. Hmm. This is the plane on which the great circle will lie. Okay, suppose this is the plane on which the great circle will lie. Let us draw this great circle. Maybe this may be the great circle. Okay, so this may be the great circle of this sphere. Hmm. Now, how to obtain the equation of this what we need to do, find the equation of the sphere. We need to find out the equation of this sphere. uh, we are given that the equation of the circle is this. We are given that the equation of the circle is this. Huh? So the equation of the circle is actually the intersection of this sphere and this kind of this kind of plane. Okay, so that can be written as the formula is plus lambda into L. So required equation of the sphere can be written as is plus lambda into L. And you see the this if this is the required sphere, in that case what we can do, we can say that is plus lambda L is equal to 0 is the equation of the required sphere. And how to find out the lambda, that is a challenge. And in order to find the lambda, let us try to find out the equation of this circle. What would be the center of this circle? Let us try to find out the center of this circle. This is the center of the circle, and this center must be is equal to the center of the sphere as well. As because it is a great circle, therefore this center must be is equal to the center of the sphere. And this is the expression of s plus lambda L. This is the expression of s plus lambda L. Got it? So this is s plus lambda L. This is the required sphere. So the required sphere, what would be the center of this required sphere? If we write this expression in this way, you see x square, and what is the coefficient of x over here? The coefficient of x is equal to twice lambda. So minus lambda would be the x coordinate of the center. Now, how to find out the y coordinate of the center? Just try to look at the coefficient of y over here, 7 plus 3 lambda, that is the coefficient of y. So half of this quantity with the negative sign, this minus 7 minus 3 lambda into half, this would be the y coordinate of the sphere. And similarly, the z coordinate of the sphere would be obtained by observing the this coefficient of z. So z minus twice z, over here 4z into 4 into lambda and minus 2, that is the coefficient of z. So in from this expression, hmm, half of this expression 4 lambda 4 lambda minus 2 this kind of expression with a negative sign, that will be the z coordinate, and that becomes is equal to this kind of expression. That becomes is equal to 1 minus twice lambda. So from this result we can find the z coordinate. So in this way we find the x coordinate, y coordinate and z coordinate of this sphere. And clearly this center point must lie on this plane, and we are given the equation of the plane to be equal to for this kind of equation, twice x plus 3y plus 4z is equal to 8. And therefore this center must lie on this plane. And so we can put these three quantities over here in place of x, y and z and solve them. Ultimately we will be able to get the value of lambda. Over here lambda becomes is equal to -1. So if we put the value of lambda is equal to -1 in this equation of the sphere, then we will be able to find out the equation of this required sphere. All right then. So that's all for today. Thank you.